Good day, doctor. I'm Kavitashri Anaparpan K. Tanabalan. My matrix number is 24006-159/1. Together with Yashwini Raghavendra Thayalan, matrix number is 24006-074/1. And Harini Vijay Kumar, matrix number is 24006-106/1. Would like to explain about the assignment of KIB2016 Fluid Mechanics and Transport Processes in Biomedical Devices. Our assignment topic is differential analysis of fluid flow in a biomedical tube.
Introduction. Pacilio flow describes steady, incompressible, laminar fully developed flow of a Newtonian fluid in a circular tube. The velocity profile is parabolic with maximum velocity at the center and zero at the wall due to non-slip condition. Flow rate depends on pressure gradient, tube radius, viscosity, and length. Objectives. First, to analyze fluid flow in a small horizontal tube using differential analysis under laminar, steady, incompressible, and fully developed flow conditions. Second, to determine the velocity profile of the fluid inside the tube and understand the parabolic nature of laminar flow. Third, to calculate key flow parameters including maximum velocity, average velocity, volumetric flow rate, and wall shear stress. Next, to design and conduct a simple experiment to measure the average velocity of fluid flow in a tube under similar conditions. Then, to compare theoretical results with experimental results and evaluate the accuracy and limitations of the assumptions used in analysis. And finally, to strengthen understanding of how differential fluid analysis is applied in biomedical engineering systems such as tubing and fluid transport device.
These are the materials and apparatus used for this experiment, which are water bottle, bottle cap with a hole, water, timer, plastic straw, measuring cup, and a container. Before we start, we prepare for a small setup, which is placing a digital timer, prepare a clean, empty plastic container to collect the water, fill up water in a plastic bottle, equipped with a straw inserted in the bottle cap. When we start the experiment, set the digital timer for 10 seconds, invert the water bottle directly over the empty plastic container, simultaneously start the 10-second countdown timer and allow the water to stream out freely from the water bottle into the container. Maintain a steady hold on the bottle for the duration of the countdown, ensuring all the dispensed water is captured. As soon as the timer reaches zero, pull the water bottle away and stop the flow immediately. Retrieve a calibrated measuring cup and carefully pour the collected water into the measuring cup and precisely read and record the volume of water dispensed. When we start the experiment, set the digital timer for 10 seconds.
Next, this slide shows the results and calculation obtained from our experiment using the straw model. First, the time taken to collect the water was recorded as 10 seconds and the volume measure was 8 milliliter. When we convert it into meter cube, it's 8 times 10 to power of negative 6. For the measurement, the length of the straw was measured as 20.3 centimeter, which is equivalent to 0.203 meter. The diameter of the straw opening was 0.6 centimeters, so the radius used for calculation is 0.003 meter. Using these values, we first calculated the flow rate using the equation Q equal to V divided by T, where Q is flow rate, V is volume, and T is the time. So when we substitute Q equals to 8 times 10 power of negative 6 divided by 10 seconds, we got the flow rate is equivalent to 8 times 10 to power of negative 7 meter cube per second. Then we calculate the cross-sectional area of the straw. A equals to pi r square. A equals to pi times 0.003 square. So area we got 2.83 times 10 to power of negative 5 meters square. Then we using this flow rate and area, we calculate velocity of the water. Velocity of the water equivalent to flow rate divided by cross-sectional area of the straw. So V equivalent to 8 times 10 to power of negative 7 divided by 2.83 times 10 to power of negative 5. So the velocity of the water we got 0.0283 meter per second. This calculation helps us analyze the fluid flow characteristics through the straw model and understand the relationship between flow rate, area and velocity.
Conclusion: this experiment applied differential analysis and Poiseuille flow to study laminar fluid motion in a small tube. A parabolic velocity profile was observed and key parameters were derived theoretically and compared with experiments. Results confirm fluid mechanics principles with minor deviations due to experimental limitations and non-ideal flow conditions.